Welcome to the solutions to the Regents Physics Current Electricity problem set, problems number 10 through 16. All right, let's jump in and start with number 10 here. A 4,000 watt clothes dryer is connected to a 220 volt circuit. How much current does the dryer draw? 4,000 watts, due to the units you recognize is the power. 220 volts you would recognize due to units as the voltage, V. How much current does the dryer draw means how much current does it use, and that would be capital I. So what's the equation that connects these three variables? It would be P equals V times I. Substituting our power, 4,000 watts, equals our voltage, 220 volts, times the current, divide by 220, we have a current of 18.2 amps. You notice that's a 220 volt circuit, which is twice the value of normal wall electricity. Very typical for an electric dryer. Okay? All right, on to number 11. A resistance of 60 ohms has a current of 0.40 amps through it when it's connected to terminals of battery. What's the voltage of the battery? Here we have resistance R, 60 ohms, current I, 0.40 amps, and they want the voltage of the battery, V. Well, from Ohm's law, which is R equals V over I, if we solve that, V equals I times R. Substituting in our values, I is 0.40 amps, R 60 ohms, and 0.4 times 60 is 24 volts. Our answer to number 11. Number 12, a voltage of 75 volts, that would be V, placed across a 15 ohm resistor, that would be R. What's the current through the resistor? Again, with Ohm's law, they're asking you to use Ohm's law, solved and isolated for the current I. So I would be V divided by R. And we take the voltage, 75 volts, divide by the resistance of 15 ohms. And that would give us a current of 5 amps. On to number 13. A person with dry skin has a resistance from one arm to the other of about 1 times 10 to the 5th ohms. When the skin is wet, resistance drops to about 1.5 times 10 to the 3rd ohms. Refer to the table below. We look at the table, which is a table of currents where there are possible side effects. Discussing damage caused by electrical shock. And you notice that it only takes 1 milliamp for you to feel a mild shock. At 5 milliamps, the shock is painful. At 15 milliamps, you would lose muscle control. And at 100 milliamps, that can kill you. So A, what is the minimum voltage placed across the arms that would produce a current that could be felt by a person with dry skin? So a current that can be felt is 1 milliamp. So they want to know the V value. Okay, we know the I value from the chart, and they gave you the resistance from one arm to the other of the dry skin, which is up here at 1 times 10 to the 5th ohms. Sounds like Ohm's law. Solve for V would be V equals I times R. Go ahead and sub in the values. 1 milliamp would be 1 times 10 to the negative 3 amps. Milli is 10 to the negative 3. And times your resistance, 1 times 10 to the 5th. The voltage required to do that would be 100 volts. 1.0 times 10 to the 2nd volts to the appropriate number of sig figs. B, what effect would the same voltage have if the person had wet skin? So now we're going to give the person this same 100 volts, but now their skin is wet, which drops their resistance to 1500 ohms. All right, so we need to find the current here and then use the chart to compare to see what would happen. So I equals V divided by R, 100 volts, divided by 1.5 times 10 to the 3rd ohms, would give you a current experienced of 6.7 times 10 to the negative 2 amps, which would be 67 milliamps. And of course, from the chart, this means that you will definitely lose muscle control but you might live. Okay, definitely on the high side there, approaching extreme danger in that circumstance. Okay, amazing to think about. Same voltage, can barely, mild shock can be felt in the first circumstance, but with wet skin, you can be approaching near death in that circumstance. All right, number 14, you need graph paper for this one. Some students connect a length of nichrome wire to a variable voltage supply that could produce between 0 and 10 volts across the wire. They then measure the current through the wire for several voltages. They record the data showing the voltages used and the currents measured. These are presented in the table below. A wants you to, for each measurement, calculate the resistance. Then it wants you to graph voltage versus current. And does the nichrome wire obey Ohm's law? If not, specify the voltage range for which Ohm's law holds true. Okay, so A, for A, you're going to take R equals V divided by I. And to get all these values here, use Ohm's law, R equals V divided by I. My values are not shown in the table, but they are shown on the graph. So just make sure that your corresponding resistance, in order to make sure you're correct, that the corresponding resistances match up to the values that you would see on the graph there. Okay? And then you graph voltage versus current, voltage on the y-axis, since it's the before the verses, and current on the x-axis after the verses. So voltage versus current, and you plot your data, and it looks like a pretty good fit. The data is pretty tightly correlated. And the answer to C here, does the nichrome obey Ohm's law? Well, it appears to, because the fit is linear and therefore indicates that voltage and current were directly proportional. But if you look at the data, the analysis of the data shows that as voltage increases, the resistance of the wire also slightly increases. Once you had your resistance values here, you'll see that the wire does not quite obey Ohm's law. And it's probably going to do that at these low voltages, but I'm going to guarantee you that as you continue at higher voltages than ones that were tested here, that this definitely would not. Nichrome has a high resistivity. If you look it up on the reference table, and nichrome is the wire that's used in your toaster. So we know after a while it gets so hot because of its resistance that it glows and gives off heat, which we then use to toast our bread or bagels or whatever. All right, let's continue moving on here. Number 15 was the maximum current that should be allowed in a 5-watt 200 ohm resistor. And again, 5 watts is power, 220 ohms is resistance. So using the appropriate equation that relates power, resistance, and current, that would be P equals I squared times R, right off the reference table. Substitute, we got 5 watts equals I squared times 220 ohms. Divide 5 by 20, and then take the square root to get a current of 0.15 amperes. Okay? And lastly, number 16. A wire in a house circuit is rated at 15 amps and has a resistance of 0.15 ohms. What's its power rating, and how much heat does the wire give off in 10 minutes? Okay? Well, on this one, we have current and we have resistance, and they want power. So the power equation we would choose that relates all three is P equals I squared times R. This would be 15 amps squared times 0.15 ohms. And when you do the calculation, you should get 34 watts. How much heat does the wire give off in 10 minutes? And this is assuming that all the energy that's in the form of electrical energy gets transferred to heat, which it doesn't, but they're assuming that in this case. The energy, electrical energy, is calculated by power times time. So we know our power, non-sig fig, was 33.75 watts, and 10 minutes, 10 times 60 seconds in 1 minute is 600 seconds. We have to use seconds in that, not minutes. So 33.75 times 60 seconds gives us 20,300 joules. Okay. Now, this number of joules again, in this, they're assuming that all the electrical energy gets converted to heat energy, and though that's not true, you have to make that assumption in this question because they don't say otherwise. So there you go. There are the solutions to problems 10 through 16. More to come on these concepts as we do problems 17 and 18 together in class tomorrow.